Yep, so I'm going to talk about projectiles. And uh, I posted this tweet uh, some time ago with this basketball aiming cannon. Um, so I wanted to talk about how I did the math behind this and also how you can hit moving targets too. And then later we're gonna live code a people cannon. Um, you can see I had a lot of fun making this.
This is one of the best things on Twitter all year, I have to say. Especially the smiley face in the basketballs. That was an awesome touch.
I think what's also great about this last bit is that I think because there's so many basketballs, none of them are actually landing in the basket because they're colliding in midair and bumping each other out of course. But yeah. Okay, so should we talk about how this works? So if we have a cannon, I'm going to draw a little cannon here. That's good enough. And we want to hit some target, right? So we're going to assume that the cannons or the initial firing velocity is constant. So really what we're trying to find is just the launch direction in order to hit this target over here. So in order to figure this out, I want to imagine a sphere or a circle around the cannon, sort of expanding over time, right? So it's getting bigger and bigger, and at some point, it's going to touch the target like that, and then if we draw a vector from the cannon origin to the target, then we have our launch direction. So we could express this as see the distance between the target and the cannon D would be equal to, let's say, S for the cannon's firing velocity times T. But of course, this does not account for gravity, right? So if you try to use this firing angle, the cannonballs will probably just go somewhere like that. So instead, we can imagine that this circle, as it's growing, it's also accelerating downwards in a way. So as it's growing, it's also falling like this or something. So we could add an acceleration term to this. So instead, I'm going to say, let's say P for the relative position between the target and the cannon. And this will actually be a vector. And then we can add, say, the 1/2 times the acceleration times t squared, and then take the distance of this vector. Now, when I said the circle was falling while it's expanding, I have a better way of visualizing that. I have this little scene prepared. So if we run this, if I start it now, you can kind of see the effect there. So the circle expands, and as it's expanding, it's also falling due to gravity. And you can see here it's touching the target. And so if we draw a vector from where the center of the circle is to the target, we get our launch direction. And actually, because of the acceleration, we actually managed to hit the target twice. So we also hit it there before it doesn't ever hit it again. Now, of course, this circle thing, what it actually represents is every possible shot we can take. So really, this represents if we fire in any direction, the projectile will be somewhere on the surface of the sphere at all times. Right. So that's what we're modeling here. And actually, up here, I have it up here as well. I also have, in the final equation, I have a third term for the velocity. This is the relative velocity between the projectile and the shooter. And the relative velocity is, in this scenario, with the cannon, it's actually going to be 0 because the target is static. So this velocity term is used for the moving targets, which I'll get to. So down here, I want to expand this so we have for each individual axis. So that's what I'm doing here. I'm expanding this so I have the px, vx, and ax. Here are the y and then the z components. And to get rid of that square root we might get from this distance function, we can just square both sides. So that's what I'm doing there. And we can expand this further to get this thing. And I've written this in, as you can see, it's written in a polynomial form. So we have our t4, t to the power 3, t2, and t here. And this does look a bit like a mess at first, but there's actually something really nice about these coefficients here of this polynomial.
Sorry, where did the t to the 4 come from?
Right. Yeah, that's what you get when you expand all this. You get a quartic, a 4-degree polynomial.
I don't see how. Oh, there's a typo in your formulas. That's the t squareds.
Yeah, the t squareds. Yeah, that's right. Sorry. All right, there. Yeah, so this becomes a 4th degree polynomial. So actually, we already know all of these variables. And what's also nice about these coefficients is if you look at this is just the dot product. If A is a vector, this is just equivalent to A dot A, this bit right here. And this is equivalent to V dot A, right? And here is V dot V. And in fact, all of these are dot products. And this S term comes from this S here, which I subtracted from both sides. And here's P dot A, right, this bit. And P dot V. So it all comes down to dot product. So it's very nice to, it's very easy to calculate these values. And once we have all those, we just need to solve for t. So this comes down to a root finding problem with a 4th degree polynomial. So for 4th degree polynomials, there are actually known solutions, or there are known formulas that can get all the roots.
Sorry to
but they are
interrupt,
very long.
but why are we solving for t if you just want to know for which value of the relative velocity there is a solution? Is that right?
Right. We're solving for t to find, at which point in time does the circle hit the target? And when we have that, then we can find out where this point will be at that point in time. Now, of course, this is a static point, of course, but the projectiles are accelerating downwards due to gravity. So if we calculate the relative position between the projectiles and the target positions after that time t, then we can get this direction, this firing direction. Does that make sense? Yeah, okay. So like I mentioned, there are known quartic formulas, but they're very long. This doesn't even fit on my very large monitor. You could type this whole thing out in code, but I would be quite afraid of getting like one variable wrong or getting a sign wrong or something, and it just doesn't work. So instead, I'm going to be using a root finding algorithm for solving for the time. And what's nice about the root finding algorithm is also if you have larger degree polynomials. If you have a polynomial of 5th degree or higher, there are no known formulas. So if you have projectiles that experience like change in acceleration, right, then you're going to have jerk in your equation, and then it's going to be I think a 6th degree polynomial. So a root finding algorithm will be necessary in that case. Now for root finding, we could use a root finding algorithm like Newton's Newton-Raphson method, which could work. But the problem is that it only allows us to find one root at a time. And that's not suitable for our case because we want to find all the roots. Because, for instance, if we're firing at this projectile, then one of the trajectories might look like this, and the other one might look like that. So you have a low and a high one. Now, obviously, this trajectory would hit the target in a shorter time. So if you wanted to find the trajectory that has the shortest positive time, then you have to find all the roots so you can pick the one that is in fact the shortest. Because if you did something like the Newton's method, it relies heavily on your starting, where you pick the starting position. So there's really no way to know which root you'll actually end up finding. So instead, we're going to use a root finding algorithm, a global root finding algorithm instead, which finds all the roots at once. Now, I saw this method on a YouTube video, and the guy who made that video, he said he couldn't actually find where he couldn't find a similar method anywhere else. So there's a chance that he might have invented this algorithm. I don't know, but it goes like this. So if we have, this is a 4th degree polynomial, and we've got 4 roots. So what I'm going to do is I'm going to take the derivative of this, and the derivative might look something like this. So it's going to intersect the x-axis wherever the peaks and valleys are, and then it's going to go flat here, and it might look something like this. Now, if we look where this polynomial, this derivative polynomial hits the x-axis, you'll see that it actually corresponds with the peaks and valleys of the original function, right? Now, interestingly, these points right here actually encapsulate the points of the original function, the roots. And so here, for instance, if we take this root right here, so we now have, if we know where the peaks and valleys are, then we have a negative point on the original function and a positive point. And because this function is continuous, we know by the intermediate axis or the intermediate value theorem that this function is going to intersect the x-axis at some point between these 2 points here. So now we can use we can use a binary search, or as it's known in the context of mathematics, the bisection method, which is where we keep dividing the possibility, or we keep dividing the space in half of where the point could be until we're happy with the precision. It works something like this. If we say we set the minimum value here and the maximum, then we pick the midpoint. And then we say, where does this point lie on the function? Maybe it's right here. If this point is positive, right, then that means we have to move this way. So we take this line here, we just move it here instead, and then we pick the midpoint again. And we can do the same thing over and over. So this time it's negative, so we have to move up here. And we can continue doing this until we're happy with the position. And we can do this for all the roots. So we know that between this valley and this peak, there's a root. Between this peak and this valley, there's a root. And for these outer points here, for these points, it's a little bit trickier because we need, of course, we need a point somewhere out here where we know the function is positive. And we don't, obviously we don't want the search domain to be too large, because then it'll take a lot of iterations to actually find these points here. But we also don't want it to be too small, so we don't accidentally pick these outer points where they actually don't encapsulate these points, and we won't be able to find them successfully. And there I'm just thinking for our projectile example, if we imagine we have a cannon and if we fire straight up in the air, the time it takes for that projectile to land on the ground again, we can use that as the time, the maximum time, right? That's one way you could do it. If you assume that there's always a ground that the projectile is going to land on, it's obviously not going to make sense to have solutions that end up beneath the ground. Now, of course, this whole thing assumes that we also know the derivative of this, or sorry, we can solve the roots of this derivative function, right? So how do we find these points? Because we need to know where these points lie in order to know where the peaks and valleys are. And the solution to that is just to take the derivative again. So we take the derivative of the derivative, which might look something like this. And then, now this is a second degree polynomial, which is still, there's the quadratic formula we could use. But I would even go so far as to say we could just take the derivative one more time until we have a straight line. And a straight line is trivial to solve. So we can have that point there. And given we have those outer points that we picked somewhere outside the function, or somewhere out here, wherever our search domain might be. And then we can find the points of this. We can work back up the chain, right? So we can find the points of the quadratic, and then we use those points. Those points encapsulate the cubic, so we can find the points of the cubic, and then finally we can find the points of the original function. So that's sort of how the root finding algorithm works. Did any of that make sense?
Yeah.
Yeah.
That was cool.
Okay.
I was thinking that maybe there's, rather than using hitting the ground, which is fine, but maybe you want to consider cannons that are shooting down into valleys or something. You could presumably get a pretty reasonable estimate if you use the scale of the gap between, your first red dot on the blue curve to the right of the y-axis, and the gap between that and the next valley. If you take 2 lots of that, you might be able to prove with a little bit of math that that's definitely greater than the next root.
Right.
Maybe take 3 times that. I don't know. If you could do some rough inequalities there and probably get something like that. But yeah, obviously that's not necessary.
Yeah.
Yeah, I've seen a similar algorithm used. Sometimes you want to get you just want to isolate your roots. Like you don't actually care where they are exactly. You just want to get them within certain intervals so that you can then do interval arithmetic, and you can do a similar trick where you use the optima of the derivative to, or the zeros of the derivative to basically isolate your roots. So it's kind of related to that, I think.
Yeah.
Yeah, I think this is an excellent example of reasoning with calculus. I'm teaching Calc 1 next semester, and maybe I'll just give the job to you, Mathias.
I actually have to do this for Caterham. I had to do this exact thing, but for a 6th degree. And this is cool. I didn't realize you could just keep taking derivatives until you can actually solve one of the polynomial roots. So thank you for this idea.
Yeah, you're welcome. There's actually a little bit. There's actually a slight pitfall, of course, if you have a 4th degree polynomial that doesn't have 4 roots. Then what you do? Actually, an even worse case, if you have a 4th degree polynomial that doesn't even have or that doesn't even have 2 values. So it never goes to so right here at this point, it never goes to a positive derivative. Then the derivative is not going to intersect the x-axis there either. So you're only going to get, what the derivative of this would be. Let's see. It goes something like this, right? And then something like that, yeah. Or actually, no. Wait. It's going to go down, and then it's never going to come back up. So in this case, it actually doesn't matter too much, because if you can find this point, even though it doesn't intersect over here, it's actually fine, because this point is enough to find these 2 points, given that you also have these 2 extra points outside here. And the algorithm I've written does account for this too. And even if there are no solutions at all, if you have a fourth degree. It doesn't intersect the x-axis ever. That's fine too. You just get no solutions, and you can interpret that as saying, well, maybe the target is just out of range in that case. And also, of course, this axis here represents time, right? And this right here is 0 time. So if you manage to find routes that are outside here, these are actually negative. They have negative time, right? Which doesn't really make sense. So after you've found those routes, you can just discard those and only you only really care about the positive routes. Right. So I guess for the moving projectiles, it's actually the exact same equations. So last off, or when we did the static target thing, we just leave the relative velocity at 0 because the target isn't moving. But if it is moving, let's say you have a cannon again, and you have another cannon, and this cannon has shot a projectile. It's flying towards you, and you want to find out, how can I intercept this cannonball? So in this scenario, the relative acceleration, before, the relative acceleration was gravity, right? The gravitational acceleration. But in this case, because both balls are accelerating down at the same speed, that means their relative acceleration comes out to 0. It doesn't matter if two balls are accelerating down or not. If they have the same trajectory that they're going to hit each other, then whether or not there's gravity or not doesn't matter. So we can just leave the acceleration at 0, and instead the relative velocity, which is just this ball's velocity minus this ball's velocity. And that's how you do moving targets.
Wait, so why is that true that if they're those trajectories, like if those straight lines meet, then their parabolic arcs will always meet?
I I don't have a better explanation of this than just intuition, basically. But yeah, but yeah, like that if they're moving, if they're not moving at all, and they might hit like this, right? But if they're both moving down at the same speed, then they might as well not be moving at all, relative to each other, at least.
Okay.
But in the static example, we had, this one is accelerating, but this one is not. So we have to account for acceleration in that case. And this example here actually shows, I can unanchor this, and if I give it some velocity, say maybe 5 there, I think I can, yeah, still works. I think I can actually get it to a point where it strikes, where there are 4 possible shots it can take, maybe. I might have to unanchor the base plate because it might hit the ground. But if I do something like this, then it hits there. So that's 1. Okay, it's not fast enough. Give it more speed. So 1, That's 2. And well, since it's a 4th degree polynomial, it should be possible to find some configuration where it strikes 4 times. Anyways, should we work on people cannons now?
Yes, that sounds awesome.
Yeah, I actually have this little scene set up just for the occasion. So here's me. And this is where I live. This is my home island. And I've been living off of the coconut from the palm trees. Very delicate. Unfortunately, there's water in between, and I don't know how to build a boat. I also don't want to swim because my clothes will get wet. So, what other choice do I have than to launch myself in the air with a cannon to get to the other side?
Learn to love coconuts.
Yep. So, I have a target over here. And so the goal is, I think we're going to have like a proximity prompt where you can interact with the cannon. If you do, then the cannon's going to align to hit this target over here. But then maybe after 5 seconds or so, it's going to fire and you're going to fly over here. So see, I actually left some, I actually just copied the old, this was from the basketball example. Yeah. I actually meant to code this from scratch, but I don't know if we have time.
I think this is great, but could you zoom in a bit? It's a bit hard to read for the stream.
Oh yeah. Okay. Yeah, so this was from the basketball example, but we're gonna have to modify it to work with players, of course. So the way the cannon is set up, I have I have the cannon model here with a cannon script inside. Then I have this barrel model and the base. And the base contains a pivot. So I like for the cannon to rotate the whole base, rotate around the y-axis. Let me turn off join services. And oh, now all the parts have welds in them. I don't want that. And so inside the barrel is another pivot so that I can turn the barrel up and down. So I think I would actually like the cannon to visually point towards the firing angle. I also added I didn't know what to call this, so I just called it the seat, which is where I want to weld the player to this part before the cannon fires. Okay. So maybe I'll start with a proximity prompt. I haven't actually used these before. That's always helpful to have your... No, that's not what I want. Okay, that's not too bad. Yep, so if we have a proximity prompt in there, I guess we could define the seat. And all these other definitions is just this is just a model. We have the barrels, and then we have these are the pivots that I showed earlier. We can have the seat be, let's see, barrel dot seat. And local proximity prompt be seat dot proximity prompt. Call this launch. And the polynomial roots. This is the function. This is a module that just returns a function. It looks like this, which just returns the function that actually calculates the roots from a list of coefficients. And this algorithm, I'm not sure if I'm going to go over this just now, but it's using the algorithm I explained. It actually works for any number of coefficients too, which is pretty cool. But I could make this available after the stream if needed. Let's see. I have a velocity attribute, which is not actually in this model, so we could add that. Or maybe it's in the script. Oh yeah, it's in the script, okay. Get rid of this.
Just a little.
Let's do the.
Oh, sorry to interrupt. I just wanted to add a little bit of a historical note. I'm not sure if you're aware, but this exact problem of hitting a moving and possibly accelerating target with only samples of observations of it from the ground. During the Second World War, this was a problem that Norbert Wiener worked on, and it was the origin of cybernetics, and through him, what we now call artificial intelligence. So this is a very important historical problem, hitting a moving target from a cannon.
Yeah. Let's see. So for the proximity prompt, right? Okay. So we could down here. We could say proximity prompt dot, what was it? Triggered. Connect a new function with the player who, passing the player who used the prompt. Let's try to weld the player to the seat if we can. So we might get the player character. So local character is player dot. Then we might check if the character has a humanoid. So local humanoid equals find first or character find first child humanoid. And I guess the humanoid root part as well. If humanoid root part, then
here's a religious question. Should you just do character primary part or find first child humanoid root part? What is the official way of doing that?
Sorry, can you repeat?
So I think the humanoid root part is the primary part of the character, and I never know whether I'm supposed to get this by doing dot primary part or what you just did.
Yeah, this I mean, this is really just a precaution where this will return, instead of erroring, this will return nil if this doesn't exist. I think something would have to be very wrong if the player character doesn't have a humanoid root part, but yeah, I'm not sure if just doing dot primary part. That might also just return nil, actually. So it might be the same thing in this case.
If you access it from the character, like as a child, then you could call wait for child if you really needed to make sure that it existed.
Yeah. I'm gonna try to weld the character. I don't actually know if this is gonna work.
You
But,
could use an actual seat object and then use the sit function of the seat, and then the sit function you just pass in the humanoid.
yeah. But I guess that might be weird when the character has to fire, because then you have to like kick him out of the seat and then apply a velocity and then something else. Or you could just
Yeah.
fire the seat. Just have a cannonball with a seat on it.
It also forces you to forces the character to be sitting, which
Yeah.
probably maybe don't want.
Let's do the seat.
Are these attachments or parts?
These are parts. Well constraints don't have. Do well constraints have like D-frame properties? I don't think they have.
Okay. I guess I'm used to the
I
other
actually-
constraints where I use attachments rather than
Yeah.
parts.
I think weld constraints actually, the way they weld parts depends on how they're positioned relative to each other before when the weld constraint is created. So if I do so we can get rid of that. I just want to see what if this works. Yeah, I'm I'm just stuck here now. So maybe I want to set the humanoid root part.c frame to be equal to the seat c frame and see what that does. All right. I'm stuck in the cannon now. Maybe I want to orient it a little differently. It actually looks like we're sitting in the cannon. There we go. Yeah. Okay. So once we've done this, I want to I could probably use some of this code. Right, so this bit here is where we are calculating the coefficients, as I showed with the what was neat about the expansion was that we could just use the dot products between all the different vectors. It looks very clean and nice. And then here I solve the roots, check if there are more than one root. And actually, in this case, I just pick the last root, which is guaranteed to be positive in most practical cases. And here we calculate the direction. So this is, acceleration plus velocity plus position. So this is just calculating the total displacement of the between the target and the shooter. Now we don't want to fire a cannonball, of course. We want to fire ourselves. So let's do that. I could also, I don't think this cannon actually has sounds in it, so what if we just fire after this? It should actually align the cannon to the target, but we probably need to define the target first, which is, right now it's just this. I guess we could define this somewhere else. So we could say we have our target dot center. So we could say workspace dot target, that actually works, dot center dot position.
But you also access workspace dot target dot velocity.
Right, yeah. And this would just be 0 again. So I think the cannon should align. Okay, maybe it doesn't have enough firepower, so it's out of range. So we could just give it like a million velocity. Or maybe that's a bit excessive. Oh yeah, there we go. So we're aiming to the target now. So we might need to tweak this until we get a nice angle out of it. That's pretty good. All right, so let's just wait for 5 seconds, and then we're gonna apply a velocity to the. Also, this code is not very clean, but I might actually want to destroy, or actually, you know what? It'll make things a little bit easier for now to just put it all in one function. This weld, I think I actually want to save it somewhere out here so I can destroy it later.
Shouldn't all of this be inside that if statement?
Yeah, I guess. And then we can define the weld in there too. Then if we wait, say 5 seconds, and then say we destroy the weld, and then we say character dot, I guess character, or I guess humanoid root part dot assembly linear velocity, which would be the let's see. Well, it would be the direction that we calculated, which we calculated in here. Which I'm just going to quickly define this. Let's just do y-axis by default, and then here we set the direction. And we do this times the cannon velocity. All right. Okay.
I think there's a good chance that humanoid physics are messing with it.
Yeah, that
Probably
could
have to set
be.
the humanoid state to physics.
Right. I might just do that here. So we can take the humanoid.
Oh, or it might be the platform stand. That could work.
Oh yeah. Isn't that a property of the humanoid?
It could have been deprecated, actually. I don't know.
Try it. Okay. Well, I'm platform standing, at least.
What on earth is platform stand?
It's like a state where humanoid stops. Like there are no how do you describe it? Like there's no other forces on your character. It just like yeah, you just
You just flop.
yeah, like any other part.
I see.
That's what
Because when you
happens when you get fired out of the astro tubes, right?
Oh, yeah, I might be doing that. Yeah.
your character does like a double backflip when you turn it off.
Like, we also have this red chair that fires you in the air, and if you hit the ground at a certain angle while doing a certain thing, you would like go into this mode automatically, I believe.
It used to happen so much more. Like in old Roblox, it was hilarious. Oh, I was thinking you might be colliding with the cannon.
Yeah. What if we just move this like a little bit out? Okay.
Maybe just try jacking the velocity up. Maybe it's... I don't know if it's...
Maybe I actually need to wait a frame here.
Classic.
Because this destroy it might not. Yeah, I don't know. Well, I have run service already, so this is gonna be, again, this is really ugly, but just want to try it. Nope. Maybe it doesn't work at all. Can I set this to like 1,000? Oh, it. Okay, it does work. Ouch.
That will never not be funny.
Yeah, it's one of the best parts of Roblox, for sure.
Let's just wait a couple more times. I have no other ideas. Hey, that actually worked. Okay. And boop.
Awesome.
That's great.
Oh,
Patience is a virtue.
yeah. Of course, because it's because I'm platform standing, I can never get out of it. So I'll just
What if you just disable it after a second or so?
Yeah.
Because I think if you're far away from the land, then like I have no idea actually. Never mind.
I think I need to disable it quite late because if I disable it too early, the humanoid applies forces to the character if he's not
Yeah.
the physics state, which actually there's like a drag force as well that the characters have. So you're gonna.
Don't we essentially know the time that it's supposed to hit?
Yeah.
So you could just disable it right after we know that it's supposed to hit.
But wait, what if we
Yeah.
have 20 cannons and 30 people being shot out of them? We want them to hit each other in the air, right? Can't you just connect something to the touched event and disable this platform stand when anything inside the humanoid triggers it touched?
Yeah, I could probably do that. Right now, I actually have this this time value right here, so I'm just gonna try to wait t minus like half a second or something, and then just set this to false. Maybe the character will wake up. Hey, that worked pretty well.
I think we're coming up on the end of the scheduled time anyway. Maybe that's a reasonable place to pause, unless you wanted to put some finishing touches on it.
Yeah. Actually, I had an airplane.
I did see the shadow of that, yeah.
Yeah. The plan was for the moving targets to jump on the airplane on the way home.
Oh, wow.
With the cannon.
Maybe you'll have to come back next week and do that.
Yeah.
I second that.
Yeah, great. Yeah, thanks a lot, Mathias. That was it's even a Lego plane.
Yeah. just like a model I found.
Oh, that's cool. This was really great. Thanks a lot for preparing this. Does anybody have questions or want to make some comments before we wrap up? All right, seems not. Then, yeah, let's thank Mathias, and yeah, we'll resume next week on this, and maybe we can even put some cannons next to the Astra tubes, and then we'll really be cooking with gas.
Yeah.
Yeah, thanks, Mathias.
We can race them.
Thanks, Mathias.
Thank you.